Yesterday? Okay, we need to finish yesterday's. I'll get yesterday's back up there. That's right, I forgot about that. Thank you for reminding me. That means I didn't give you the whole assignment, did I?
No.
Okay, I'll have to adjust that. One. Let me get back into... Yes.
I heard you might order a shirt from somebody else. So.
Well, you asked me first, but you didn't ask me again yesterday, so...
Did you already buy a shirt from somebody?
No, I said you had to check. I was waiting for you to ask me.
I sold like 15 shirts.
Oh, and then well, you don't.
Sold 15.
15.
What? Yeah. What is that?
Wow.
I'm leaving this paper by 8.
Oh, that's not
You
what I
can't say
wanted.
I ask you to.
So what?
Yes, I did probably ask you.
Right now, oh.
Yeah, we're gonna finish yesterday's. We didn't finish yesterday's.
Oh, you got it. Okay, I'm leaving here soon.
Okay. I don't have any money today. I had money yesterday.
We're not running today.
Huh? I didn't even grab my purse. I realized that when I got here I didn't even have my purse today. So, oh well. Such is life. Luckily I don't live that far, so the cop can just follow me home if I get pulled over. Okay. Let's finish up where we were yesterday. So we were here. Okay. Shh. You're listening. We ended on this one. Okay. And I'm going to try to, yeah, I've got a couple to finish here and then we're going to get on to today's stuff. Okay. So, let's review what this one said. Okay. We've got, so the definition of continuity is basically if it can be continuous on a closed interval, if it's continuous on the inside of it, and it has continuity at the endpoints. So basically it's continuous all the way through here, okay, from one endpoint to the other, okay? So we're supposed to discuss the continuity of the function on the closed interval. So what I want you to do right now is I want you to graph that, okay? Well, you graph it. I'm going to try to get my oh, it's already graphed up there. You guys graph it on your calculator, okay? Make sure that that picture is right, okay? While you're doing that, I'll get this going too. Okay, we ready? So, you got it? No? Okay, so, good. So what we're going to do, in order to decide if something is continuous, okay? So in order to decide continuity, you have to test the right-hand limits. And the right and left-hand limits have to be equal for it to be, oh, and you have to have a limit. To discuss the continuity. We have to look at the left, we have to look at the right, and see if there is a limit that exists, and then we know it's continuous at the endpoints. Okay. So let's do that. So let's start by looking at, and it's going to go all crazy because I turned the calculator on. That was the one we're on. Okay, so we're going to start by writing f of x, sorry, not f of x, the limit as x approaches. So what is the value that the endpoint that it's approaching from the left side? Actually, it's not approaching that from the left side, it's approaching it as we're going towards the value is coming out from the right, because this is the point, the graph is on the right of it, okay? So, of our function, 1 minus x squared, okay? So if I were to direct substitute in that -1, we would have 1 minus -1 squared. So what would we end up with for our answer to that? 0, right? And that we verified that by looking at the picture of it, right? So it is continuous as we're going towards that one because it had a limit that existed. Okay, limit as x approaches 1 from the left side. So now think about what we're talking about there. It says that that's the other endpoint. Okay. The graph is on the left side of that endpoint, so that's why I have to use the notation of left. We're still using the same function, aren't we? Okay, so I plug the 1 into that. What do we end up with for our answer? 0. So basically I proved that it had a limit on each endpoint. And then I write, therefore, f is continuous on the interval -1 to 1, the closed interval -1 to 1. Therefore, f is continuous on -1 to 1. Okay. Put that one in your calculator. So everybody graph example 6. No, it's when they both end up equaling a limit at this point. Doesn't have to be the same on this one. Okay? We're going to talk, this is continuity at endpoints versus continuity in the middle is different. Okay? No. But you guys should come up with some ideas because the last few years I've had to come up with the ideas. Yeah. Alright, we ready? So, I'm going to correct. So we had, what does the picture look like? That? Should be similar. Mine was done with the 84. That was done with the 84 calculator version. So there's some asymptotes in here, right? It's kind of squishy. It probably looks like this and like this, right? Okay. So we have the same picture. So let's talk about -2. So -2 is right in here, isn't it? Okay. So we have to see what's happening as we're coming at it. Are we coming at it from the right side of the graph or the left side of the graph? The -2 is here, so the graph exists on the right side of it. Okay? I know, left and right is confusing. All right? I can't even do left and right unless I'm driving the car. So, yeah. I'm impaired that way. Okay. So, I'm going to go ahead and sub that -2 in and see what happens for my limit there. So we've got -2 squared minus 9. So what's -2 squared? 4 minus 9 is? So -1/5 would be that limit. Okay. So that one kind of does have a limit at -2. Let's try the limit. What's the other endpoint that I need to test? 3. Okay, 3 is over here. Is the graph existing to the left of it or to the right of it? To the left of it. So I would say from the left. Okay. So we're of the 1 over x squared minus 9. I'm going to substitute my 3 in. So 3 squared minus 9, what's 3 squared? 9 minus 9, is that going to work? It does not exist. So is it continuous on this particular closed interval? No. But if I switched that closed interval from -2 to 2, it would work, right? Because I have a limit that exists. I would have a limit that exists. Does that make sense? So if the limit doesn't exist on one of the endpoints, it's not continuous on that particular closed interval. Okay, and again, we're going to talk about another kind of continuity here. We're only talking about at the endpoints. Okay? Oh, good, the battery's going to die. Is not continuous. on -2 to 3. I gotta go get the cord. So therefore, G is not continuous on the interval -2 to 3. Okay. Okay, let's keep going. Everybody got that one?
No. Sorry, I was talking with Connor.
You were talking?
Yeah, he's distracting us.
All right. I want you to go ahead and put that one on your calculator. Okay? All right, do we agree with my picture? Yeah. Okay, so let's talk about the question that it's asking. Find the values, if any, at which f is not continuous. Is there anywhere where it's not continuous? No, so this one is continuous. If it's not continuous, there's a hole, there's a gap, it's going to infinity, it's got to go up and down, right, towards infinity. All right. What's your work on that problem? Sketch the graph from your calculator. Does it have to be perfect like that one? No. Draw a sketch that proves to me you understood what it looked like because you put it in your calculator. Okay? Caesar, what's wrong?
For this homework, are we gonna need like a graphing utility or something?
Do you have a computer at home?
Nope.
No. Do you have your phone?
Yeah.
There's probably an app for a graphing calculator for your phone. Okay? Try Meta Calculator. Sometimes that one comes up. That one came up a number of years ago. Okay? So, yes, you may need one. Okay? It is a requirement of the AP test. Okay? That we do teach graphing calculator. All right, let's talk about this one. All right? So, here's what I want you to do. I want you to go ahead and graph it. So, everybody graph that one again. Caesar, do you have an Apple or a Android? Apple. I'll look. I do too.
Oh yeah.
Okay. Shh. Do we have it graphed?
Yeah. It has
Okay.
it's separated from the starter.
All right. So it does have something going on here, but you know what? Our calculator can lie to us. There might be more discontinuity than that. So let's actually let's factor this guy. Okay. So we've got x plus 4. Shh. You tell me what's the denominator factor into? X minus 5, x plus 4. Good. So what happens here? It cancels. When it cancels, what is it? We talked about it the other day. Cancels, good job, is a whole. Okay, is a whole. When it's left behind, that means in the denominator, right? It's a vertical asymptote. So, let's answer the question now. Find the x values, if any, at which f is not continuous. There's two places where it's not continuous. What are they? X equals what? Not -5, but 5, right? So set it equal to 0 and solve it. Do I really need to write that work down? No. Okay, where's the other place where it's not continuous? -4, good. Because those are where I either have a hole because I canceled it or I have an asymptote because it was left behind in the denominator. Then it says which of the discontinuities are removable, okay? So at 5, it is non-removable. Why? What is it at 5? It's vertical asymptote, right? So non-removable, and you write vertical asymptote. Okay. What about at -4? What was a -4? A hole, because it canceled, right? Is that removable or non-removable when it's a hole? Are you able to see the hole on your calculator? No. Okay. Because the calculator has all those little pixels so close to each other that it doesn't pick up the hole. Okay. So it actually probably doesn't graph it. It actually cancels out and just graphs this. It doesn't graph the whole the whole piece. Okay. All right. That finished those notes, right? Okay. So let's go ahead and switch to the ones. Let's flip to the ones that were for today. We'll see how far we can get on those. Okay. So get that essential question written. What problem number did we end last night's homework on, guys? We just did 1 to 19 odd? Okay. All right. See how far we can get with this one. Okay, we ready? Okay, here we go. So we're going to talk today more about using the continuity of a function using intervals. Okay. So we're going to look at the inside continuity versus the endpoint continuity like we were just doing. Okay. Do we need to fill in? Or is that already filled in for us? It's already done for us. Okay, so I was nice apparently. So if b is a real number, and f and g are continuous at x equals c, then the following functions are also continuous. So as long as your functions are continuous, if you multiply by a number in front of the function, if you add the two continuous functions together, if you multiply the continuous functions, or if you divide the continuous functions, as long as the denominator is not 0, you still have continuous functions. Okay? Types of functions that are continuous at every point in their domain. Some numbers are not in their domain. Okay? As any polynomial. That's a generic form of a polynomial. Okay? It could be a squared, it could be a cubed, it could be a fifth, it could be something else. A rational is a polynomial over a polynomial. A radical is continuous in its domain. Because remember, most radicals... Oh, it's not. I don't have that pen going. A lot of... like a square root function looks like that, right? It's continuous as long as you're talking about its domain. If you're talking about over here, that's not in its domain. Okay? And then trig functions are continuous, again, within their domain, because remember what secant and cosecant look like that, and these here are not, the asymptotes are not technically in the domain. Okay? All right. So it wants me to find the x values, if at any, of which f is continuous, and which of the discontinuities are removable. Okay, so there's 3 things. You might want to write this out in the left-hand column. Okay? So there's 3 things we have to test every time to decide if something's continuous at a point. So this is continuous at a point. 3 things. Okay? Should probably put this in the actual notes. It is defined at f of c, meaning it has a value there, okay, somewhere. The second thing is the limit as x approaches c exists. That means I have to test the right and the left-hand limit, okay? And the third thing we have to look at is making sure number 1 and 2 are equal to each other. Then we know it's continuous. So we're not going to use our calculator to look at these things. Okay, we're going to do this algebraically today. So these two things have to be equal. All right, so let's talk about, so I'm gonna number off my steps a little bit here. Okay, so the first thing I'm gonna do, I'm gonna look at that it is defined. So I need to evaluate it at what value? 1. Okay, notice the instructions were the same as what they were in the last part of the notes, right, of yesterday's. So I'm only gonna look at where it's equal to 1. So do I want the top branch or the bottom branch? Bottom branch. So I'm gonna look at f of 1. I'm plugging into this function here, so I'm going to plug in 1 and square it. What do we get for that value? 1. Good. Okay, so I got the first one. I know it's defined at 1. Now I have to examine the limit. And to get the limit overall, I have to look at the right-hand limit and the left-hand limit and make sure they're equal. Okay? So I'm going to do the limit as x approaches 1 from the left. So is the left the top branch or the bottom branch? Top. Good. So -2 times, oh sorry, I write it out 2x plus 3 and then I plug in. So I plug in 1. What's 1 times -2? -2 plus 3 ends up being 1. Good. Now I have to look at the limit as x approaches 1 from the right. What? It is the same, isn't it? Right? Didn't I kind of already do that up here? Yeah, but officially I have to write the work, right? So we know that x squared or 1 squared is going to be 1. You don't necessarily have to write all that down. At least write that it's equal to 1. So do the left and the right hand limits equal each other? Yes. So the limit overall, and you have to write this, it's like we're writing a proof, okay? You have to show them your thinking. The limit of f of x overall is equal to 1. So does the value at 1 and the limit at 1 equal the same number? Yes. So therefore we know that it is continuous. So here's how we write step 3. Okay? It's a little bit of a sentence, kind of a conclusion to our proof. F of 1 equals the limit as x approaches 1 of f of x. So, oops, I forgot my therefore symbol. Therefore, f of 1 equals the limit as x approaches 1 of f of x. So f is continuous at x equals 1, and f is continuous everywhere. Because they didn't give me any endpoints or anything, the only point of possible discontinuity was at 1. So if it was continuous there, that means it's also going to be continuous everywhere. Okay? All right. I'm not going to change it yet. I promise. Okay? Okay. All right, we good? Do I need more space in that part? Yeah? Okay. A lot more space. I'll make that note right now. Okay. Okay. So, let's try this again. Okay? So let's do our 3 things. The first thing was we had to say it was defined. Where's the possible point of discontinuity? What number? 2. So I'm going to evaluate for f of 2. Do I plug that into the top function or the bottom function? Top, because that's where the equality is. So -2 times 2 is what? -4. Good. Now I need to test the right and the left-hand limits. The limit as x approaches 2 from the left. Limit as x approaches 2 from the right. So if I'm coming at it from the left, am I using the top branch or the bottom branch? Top branch. And didn't we already do that work? And yeah, some of it's a little repetitive, but again, we're kind of showing a proof. We're showing a line of thought. Okay. So x squared minus 4x plus 1 would be our bottom branch, and coming at it from the right. I'm going to plug the 2 in. Okay, so when I plug the 2 in there, let's see, we get 4 minus 8 plus 1. What's that? Negative 3? Are we sure? Okay. So, do the right and the left hand limits match? No. So the limit as x approaches 2 of our function does not exist. So is it continuous? No, because this number here and this number here did not turn out to be the same. So it's not continuous. So we would say for our little step 3, and do you really have to number 1, 2, 3? No, I'm trying to keep us organized so we understand the steps, okay? So therefore, if it's in this particular case, is it removable or non-removable? It's non-removable because it's not a whole. Okay, the only thing that's non-removable or removable is a whole. So therefore, it's a non-removable. Said I wanted us to talk about that. Non-removable discontinuity. Continuity at. Ooh, that was a horrible at symbol. At x equals 2. Non-removable? Because it wasn't a whole, right? I couldn't cancel anything out on the top and the bottom, so that's the only time I have a removable of is if it's a whole. Does that make sense, Caesar? Okay, good. All right. Let's take a look at example 3. Let me look up. I'm trying to decide if I want to do example 3 or not. Let me look at the notes here, or the homework here really quick and see if it's what it's like in the homework. Oh, it's only one problem. Cosecant. There's a whole bunch of them there. Yeah, we're not going to do it. Okay, so we're going to skip example 3. Yay! Skip example 3. I'm going to cross out just to get rid of that one. Okay. Example 3 is pretty ugly, and I took it out of the homework. So, oh look, I even wrote skip on there. Nice. Okay, so I even told myself not to do that one. All right, let's take a look then at example 4. Okay. Let me go to here. Okay, so notice this instructions changed. Okay. It wants me to find a constant a, so notice there's an a in here, and it wants me to figure out such that the function is continuous on the entire real line, okay? So this is the way you do that. The two things you have to do to show continuous on the entire real line. You're going to find the limit, okay, of each, so of each branch, okay? And the second thing you're going to do that is you're going to set them equal to each other. And that should solve it for you. AP loves this question. Mrs. Ballard puts it on the test, your unit test, okay? So you need to know how to do this. All right, so if you've not been paying attention, now's the time, okay? All right, so I'm going to find the limit of both branches, okay? So the limit as x approaches, what's my x value that we're approaching? 0. Good. And on the top, is it coming from the left or from the right? Left. And again, that's just notation for the most part. Okay? So, 4 sine x over x. All right, hopefully we have this memorized by now. What is the limit of sine x over x? 1. So we have 4 times 1, which ends up being what? 4. Now I'm going to do the left or the right hand limit. Limit as x approaches 0 from the right. I'm subbing into the bottom function. This says I only plug in for the x. So I'm not plugging in for the a, I'm plugging in for the x. I'm supposed to be solving for a. So a minus 2 times 0 is just going to be what? A. Good. What does it say to do in number 2? Set the left and the right equal to each other. That would make it continuous. So what is a equal to? 4. Okay, again, AP loves this thing. Okay, so let's take a look at the next one. Apparently I have a typo. In the next one, it looks like it shouldn't be 0, it should be A. Yeah. Okay. So these, oh, it says A in here. Does yours say A? Yours says 0. I don't know what happened there. So switch those to A's. Okay. All right. So what we're going to do, notice one of them is not equal to A and one of them is equal to A. All right. So I'm going to start by putting in the one. I'm going to look at the limit of both branches as we approach A, and then I'm going to set them equal to each other. Okay, even though there's not a less than, equal to, or less than symbols or greater than symbols. So the limit as x approaches A of the x squared minus a squared over x minus a. So this means that I am taking the x and I am plugging what into it? A. Okay. Can I do that just the way it looks? If I put an a into the denominator, what's going to happen? 0. So I need to, before I do that, I need to do some factoring, right? So what does the numerator factor into? X plus a, x minus a. So these guys cancel. Now is it okay for me to plug an a in? Yeah, so I'm going to go a plus a. What's a plus a? No. 2a, combining like terms, not multiplying, right? It's okay, very common mistake. All right, so that's one of the branches. I also have to plug into the other branch. The limit as x approaches a of 8 equals what? 8. What are you supposed to do with the two branches now? Set them equal to each other. So 2a equals 8, a equals 4. A will not always equal 4, just because it equaled 4 in the last two problems. Okay, yeah, no, it's not going to always equal 4. Yes?
You know when you say like left and right, what does that mean?
Okay, so let's talk about left and right again. All right? So if I've got my function, I'm going to just draw something random. Okay? There's my function. Okay? If that's my point of possible discontinuity right there, I'm coming at it, see how, if I'm coming at it from this side, that is to the left of that point, right? Okay, correct? Not right. Okay? This over here is to the right of that point. So when we're saying approaching the limit from the left, we're at the left side of the point. Approaching the limit from the right, we're on the right side of the point. Does that make sense? Okay, we good now? I know it's hard to visualize. You guys, it took me years to figure it out, and you guys unfortunately have to get it figured out by May when the test comes around, right? Or when our Unit 1 test ends up, right? Whenever that is. Okay, let's take a look at that theorem right there. Do I want to do that? Yeah, we'll do those two. We'll skip the graphs. Okay. If G is continuous at C, and F is continuous at G of C, then the composite function is continuous. So basically we can take two functions and compose them together and they are continuous, okay, as long as they originally were continuous. So it wants us to discuss the continuity of the composite function. So I am going to start by composing the two functions together. Yeah, let's just do that. So we've got f of g of x. It told me to do that right here, okay? So this means I take g and plug it into what? F. So I'm going to write my f function. And instead of writing an x, what am I going to put inside for the x? X minus 1. Good. Okay. I don't have anything that cancels, so I don't have a whole, but I do have a denominator where there's possibly an asymptote. How do we find the asymptote? What are we supposed to do? Not squared, but set it equal to 0. Now what do I do with it? Now we square it. Okay, so we got x minus 1 equals 0, so x equals 1. So, do we have a discontinuity? We just got an asymptote, right? Is an asymptote removable or non-removable? Good. Non-removable. Movable. Discontinuity. I'm abbreviating. At x equals 1. It's safer to write out. There's a few things you can. And I tell you, the DNE, you can use, and then there's a couple of others along the way. Other than that, I would write it out so you're very explicit to the graders, okay? Because you don't know who's going to grade your test. It's not going to be me, right? I might be able to understand your abbreviation, but some grader from Florida might not, okay? Who knows? I don't know I don't know where the graders come from. I know I'm eligible to grade, but I can't yet because the babies are too little, so. All right, let's talk about this one, okay? So I'm going to compose these two functions together. And this one might not be as obvious as the other one was. So f of g of x. What's my f function? Sine. So I'm going to do sine in parentheses. What's going to go inside the parentheses? Good. Okay. So here's the thing. I don't have anything that cancels, right? I don't have a denominator. Is sine a continuous function to begin with? Yeah. Is x squared a continuous function to begin with? Yeah, so what that theorem told us was if they were both continuous to begin with, then their composition has to be continuous. So we would write that it is continuous for all real numbers. Okay? Or for all reals would work. Yes?
Can we just plug these functions into the calculator and then just see like if
You could look at that. The ones that I showed algebraically, you need to make sure you can do both algebra. Okay? So I just to be sure, right? Because you don't know how on the AP test it's going to show up. My test, you might have some idea because you're going to get hints, right? Okay. All right, we're going to stop it there. We'll do the ones with the graphs tomorrow. Okay, I'll add that one onto tomorrow's homework assignment. Let me look at how I'm going to adjust this here. So don't write it. I'm going to have to adjust what's in haiku here. So let's see. What? No, there's homework.